Okay, in this video, I just want to talk about four of the equations that I have most commonly seen students get confused by or confused with each other when studying electrostatics. And a lot of times I would be grading an exam or a quiz and I would just see these equations used interchangeably. So if you're studying electrostatics and you have an exam coming up, one of my biggest suggestions is to just learn the difference between these four equations. These equations are the electric force, which is K, which is a constant, Coulomb's constant, times charge 1 times charge 2 over r squared, which is the distance between the two charges. Then there is the electric field, which is E equals K times 1 charge over r squared. And that's just the distance from the charge to where you're measuring the field. Then there's the electric potential energy, which is U equals K times Q1 times Q2 over R, but this time the R is not squared. And then there is the electric potential, not to be confused with the electric potential energy. And this is delta V. Sometimes it's just shown as V, and that equals K times Q over R. So 1Q and 1R for this one. And of course, K is Coulomb's constant, and that's also equal to 1 over 4 pi epsilon naught. So sometimes instead of K, your textbook or homework or whatever may have 1 over 4 pi epsilon naught instead of the K. So obviously these equations are all very similar and very easy to get confused, but you will be doing yourself a big favor if you just learn the difference between these four equations, and then all of the relationships between them will kind of come naturally if you just make sure that you know these four equations. Obviously, they only differ by the number of charges involved and whether or not the r is squared or not. So let's look a little bit closer at each of these, and hopefully we'll find ways to remember which equation goes with which concept. So first let's talk about the electric force. So for the electric force, this is Coulomb's law, and this involves two different charges, some distance r away from each other. This is charge 1 and charge 2. If these charges have the same magnitude, then you can actually just have kq squared over r squared. But there are often different amounts of charge, and it may be a particle, it may be a whole object that's charged either positively or negatively. But either way, there's going to be an electric force between the two objects. This actually works really similarly to the gravitational force. If you're at the point where you're studying the electric force, then you have most likely also already run into the gravitational force, which is the force equals the gravitational constant times mass 1 times mass 2 over r squared, the distance between the masses. So it would look something like this, m1, m2, and the distance between them. So these equations look pretty similar, except instead of charges, we have masses. The distance is always the distance between either the charges or the masses. And then we have a constant associated with that force. For the electric force, we have Coulomb's constant, and for the gravitational force, we have the gravitational constant. So it may help if you already remember the gravitational force equation, then you can just think of that and remember that, of course, for the electric force, you have to have two different charges, and it works as 1 over r squared, just like the gravitational force. And then we have the electric field, which is kq over r squared. So this is similar to the force, except we just have one charge. And that's because any one charge or charged object is going to create an electric field. It doesn't matter if there's another charge near it or not. It has its own electric field, just like any mass has its own gravitational field. So if we have a positive charge here, the electric field is going to have electric field lines coming off of it and moving away from the charge. And if you have just a negative charge, then the electric field lines go in the opposite direction, toward the charge itself. Now, this is what it would look like if it is not near any other charges. However, if it is near another charge, so say this positive charge and this negative charge are actually near each other, then your field lines are going to start bending and going from the positive charge toward the negative charge, like that. But either way, the field will exist with just one charge. So if you think of it that way, it may be easier to remember that the electric field equation just has one Q. And then it's 1 over r squared, similar to the force, because the force exists because of the field generated by each charge. Okay, and now we have the electric potential energy. This would work similar to other types of potential energy. So if you are holding, say you have a static charged object Q1 over here, and then you're holding Q2 over here, and say they're attracted to each other, they're opposite charges and they want to move toward each other. So basically they're feeling this force between them, and you know that as soon as you let charge 2 go, it's going to move towards charge 1. So there's this kind of built up energy, this potential energy between these charges, and that is what the electric potential energy is. For this, we do have 2 charges, and it is times 1 over r instead of r squared, and this is also similar to gravitational potential energy, which is g times mass 1 times mass 2 over r. So if you remember that, then again, this is pretty analogous to the gravitational potential energy. So for potential energy, 2 charges and works as 1 over r. And then we have the electric potential. So this is basically a potential energy per unit charge. So it has units of joules per coulomb. So this is an energy over a charge. It's like if you take the electric potential energy, divide it by a charge, then you're going to get K, Q over R. So one of those Q's cancel out. So really the best way to remember this is that it is an energy per unit charge. So another thing in general that's helpful to remember is just to know the units of each of these. So the electric force, of course, is going to be in newtons. The electric field is volts per meter, or newtons per coulomb. Newtons per coulomb makes sense because the electric field is the force divided by a charge. And then you have the electric potential energy. Like all other energies, it is measured in joules. And then the electric potential, as we just mentioned, is joules per coulomb because that is potential energy per charge. Now, as you can see, there are a lot of different ways to represent the relationships between these 4 equations, and they all involve one of the equations divided by or multiplied by an r or a q, or sometimes both. There are more relationships than just the ones on the screen here, and it's worth mentioning that the electric potential energy is equal to the force times the distance, which sure reminds us of the work, doesn't it? So when you're asked to find the work done to move a charge, this is what you're looking for. But as I said before, these are the equations that you really want to remember, because using any of these, you can find any of the others if you're given a charge or a distance, depending on the problem and what it's asking you. Let's just do a really quick example of just one of the ways to get these relationships. So for example, say you have the electric field, and you know that that is K times Q over R squared. And then you're given the charge of a second object, Q2. And then you're asked to find the force. Well, you know the electric field and you know this extra charge, and you know that the force is equal to K Q1 times Q2 over R squared. And you know the electric field, so you know then that this electric field just needs to be multiplied by Q2. So the force then is just going to be E times Q2. So usually these problems will give you, a force or electric field or electric potential or something like that, and then they'll tell you a charge or distance or whatever, and ask you to find another one of these concepts. So the electric field or the force. So if you know those first four equations, you can find any of those, the electric field, force, potential energy, and without memorizing a bunch of these. So hopefully that was helpful. I don't usually recommend memorizing everything. In physics, you should know how to figure things out by knowing how they work. I suggest memorizing as few equations as you can, and then just knowing the relationships between everything. And actually, the equations often tell you those relationships. So just doing a small amount of algebra, you can get pretty much anything from specific set of equations. For example, in projectile motion, there's 4 kinematic equations, which you can get almost anything from, and you don't really need to memorize a whole lot more than that. So for electrostatics, before you get into magnetism and everything, these are the 4 equations that I really suggest knowing the difference between. It will probably do you a world of good on your exams and quizzes.